Okay, next question, number 9, says a contractor has an 80% probability of making $70,000, 15% probability of losing $20,000, and a 0.05 probability of breaking even. What is the contractor's expected value? Now remember, for these expected value questions, we really have to think about, what is the variable of interest here. And so the variable of interest is the profit to the contractor. And then let's look at the formula for expected value. Remember, expected value of a discrete random variable is the sum of x times p of x. So what we have to do is we have to make a table where we list out the values x that the variable can take on, and then we list out the associated probabilities. And then the last column is we have to create the column for the average, which is the x times the p of x column. So one value that the variable can take on is $70,000. So he can make $70,000. And the probability of him doing this is 80%. Now, 15% probability of losing. Well, this idea here of losing means that this $20,000, he's not going to really make anything. He's going to lose this amount. So we want to make sure that this amount is negative. Okay? And what is the probability that he loses $20,000? Well, that's a 15% chance. Okay, and then lastly, and a 0.05 probability of breaking even. Well, if he breaks even, think about that. If he breaks even, then he's not going to make anything. He's not going to make anything. He's not going to lose anything. He's going to exactly break even, which points us to the net profit being 0. And so what is the probability of this happening? Well, this is 0.05. So now all we have to do is just multiply 70,000 times 0.8, and we get 56,000. And then 20,000 minus 20,000 times 0.15 gives us minus 3,000. And then 0 times 0.05 is, of course, 0. So now we can go ahead and get the expected value. So we're going to say expected value is equal to the sum of x times p of x, which is the sum of this column here. 56,000 minus 3,000 is 53,000. So that's essentially what he's can expect to make over the long term. If he builds a whole bunch of these properties, assuming he's building houses here, so he can expect in the long run to make $53,000 per property. Now, most of the time he's not ever going to make $53,000 on a single property. Most of the time, 80% of the time, he's going to earn somewhere around $70,000. And 15% of the time he's going to lose about $20,000, and then 5% of the time, or 5 out of 100 of these properties, he's just going to break even. So the expected value, or the expected profit, expected value, kind of think about this expected value, this value here, as the profit to the builder. So we would say this is 53,000. Okay, next question. Find the binomial probability of getting 3 or less defective items in a batch of 10 items if the overall percentage of defects is 40%. So you can kind of think about this in terms of binomial probability, where we have n trials. Remember, x follows a binomial, and remember there are two parameters to the binomial: n, which is the number of trials, and p, which is the probability of success. And so here, n, the number of trials, is 10. So we have a batch of 10 items. You can think about having 10 items in this batch all the way up to 10. And we're going to select all 10 items, and then we want to know what is the probability of getting 3 or less defective items in this batch of 10. So 10 is the number of trials, and then the probability of success is 0.4. And so what we want to know is we want to find the probability that the number of defective items x is less than or equal to 3. And this translates into what is the probability that the number of defective items at x is exactly equal to 0, which means there are no defective items in the batch of 10, means that all of them work, plus the probability that the number of defective items in the batch of 10 is exactly equal to 1, plus the probability that the number of defective items in the batch of 10 is exactly equal to 2, plus the probability that the number of defective items in the batch of 10 is exactly equal to 3. Now, we're going to use the binomial tables to look up these probabilities. So what you want to do is go over to your tables, and you want to find n equals 10. Remember, here's n, and then x, and then p is across the top. So n equals 10 is right here, and we want to know what is the probability of getting no defective items in a batch of 10, which is x equals 0, and p equals 0.4. So this is the first number here that we're going to write down. So we're going from x equals 0, no defective items, plus 1 defective item, plus the probability of seeing 2 defective items in a batch of 10, plus the probability of seeing exactly 3 defective items in a batch of 10. So let's go ahead and just add up these probabilities here. So we see the probability that x is equal to 0 is 0.0060, plus the probability x equals 1 is 0.0403, plus the probability x is equal to 2, which is 0.1209, plus the probability that x is equal to 3, which is 0.2150. And so we add all of these numbers up and we get 0.3822. Now that's the first part of the question, and then the second part says find the mean and standard deviation. So the mean for a binomial is really easy to calculate, and it's just n number of trials times p, the probability of success. So n in this case is 10, probability of success is 0.4, so the mean is 4, which means that on average, if we select a whole bunch of these batches of 10 items, right? So each batch has 10 items, and we do this a whole bunch of time. then on average, we can expect to see 4 defective items on average. So essentially what that means is if we count the number of defective items in this batch, say we get maybe 3 defective items, here we might get 2 defective items, here we get no defective items, here we might get 5 defective items, and then so on and so forth. We count the number of defective items in all of our batches. And then if we average all of these numbers here, right, if we take the average of all these numbers, we should get an average of 4. And that's kind of what the mean is telling us here. Okay, now the second piece here is find the standard deviation for a binomial. And again, this is real easy. It's just the square root of n times p1 minus p. So let's plug this in here. We get 10 times 0.4 times 1 minus 0.4. And we get something like approximately 1.55 for the standard deviation. So the probability here of getting 3 or less defective items is 3.822. The mean is 4, and the standard deviation is approximately 1.55. Okay, next question. An educational testing corporation has designed a standard test of mechanical aptitude. Scores on this test are normally distributed with a mean of 75 and a standard deviation of 15. So remember, we kind of write the notation here that x follows a normal distribution with a mean and a standard deviation. So x follows a normal with a mean. The mean is 75 and the standard deviation is 15. So the first question here. If a subject is randomly selected and tested, find the probability that his score will be between 70 and 97. So the first thing that we want to do here is kind of draw out a bell curve, label the mean at 75, and then find our boundary point. So we want to know what proportion of scores will be between 70 and 97. So let's locate 70 and 97. And then essentially what we're wanting to find is this area underneath the curve between 70 and 97. Now what we have to do is we have to convert our boundary points using the z-score formula. So we're going to have to convert 70 and 97 into a z-score. So let's go ahead and do the first one. And remember, the formula here is x minus mu over sigma. So z is equal to 70 minus 75 over the standard deviation of 15. And we get z is equal to minus 0.33. And then we'll convert the other one. So z is equal to x is 97 minus 75 over 15. Z is equal to 1.47. Now let's go ahead and write our equation here based on our picture. So what we're really looking for is the probability that x is between 70 and 97. Now what's happened is I've converted the mean into 0. The 97 becomes 1.47 and the 70 becomes minus 0.33. So what happens here is that the 70 becomes minus 0.33. X, of course, is converted into Z, and then 97 becomes 1.47. Now remember, we studied how to find the area under the standard normal between two values, and we talked about how when we look up 1.47, it gives us the area from this point back, and then we look up minus 0.33, and it gives us the area from that point back. So if we take the difference, and we get what's in between. So this becomes the probability that Z is less than 1.47 minus the probability that Z, Z is less than minus 0.33. And so now what we have to do is look up 1.47, positive 1.47 from table 5. So let's go over here to table 5 and look up the z-score of 1.47. So 1.4 0, 1, 2, 3, 4, 5, 6, 7 is 9292. So this area here is 0.9292, and then look up minus 0.33 from table 5, and you should get 0.3703. And so we take the difference between these two numbers here, and we get 5585. And that's the proportion of scores that will be between 70 and 97. So this area here, or percentage of scores, is 0.5585. So about 55.8% of the scores will be between 70 and 97. Okay. Second part, find the score that separates the lower 33% from the upper 67%. So we've got a bell curve here, 75, and we want to find the score, the exam score, that separates the bottom 33%. So this bottom here is 33, which means that if a person scores X, then that person has scored better than 33% of all other test takers. And that person has scored less than 67% of all test takers. So remember, the formula that we use, which comes from the z-score formula, if you do a bit of algebra, you get x equals mu plus z times sigma. And we already know mu, right? Mu is right here. And we already know sigma, which is 15 from here. The only thing that we don't know is z. Z is the only thing that's holding us back from finding the raw score X that separates the bottom 33% from the upper 67%. And what we can do is we can go over here and use the inverse norm function on the calculator to find the z-score that separates the bottom 33% from the upper 67%. So the inverse inverse norm. And the argument here is the area left, or the left area, and then the mean and standard deviation, which would be 0 and 1. So this is going to be, area left is 0.33, 0, 1, mean and standard deviation. So let's type this into the calculator and see what we get for the z-score. So we're going to do second So we're going to do second distribution and then go down to the inverse norm, and we're going to type 0.33, and the mean is 0 of the standard normal, and the standard deviation is 1 of the standard normal, close parentheses, and enter. So the z-score that we get, remember, always around to 2 decimal places, is minus 0.44. So this z-score here is minus 0.44. Minus 0.44. That's what we get for the z-score. So now we can go ahead and plug everything in. The mean is 75 plus the z-score minus 0.44 times the standard deviation of 15, and we get x is equal to approximately 68.4. And so now we can say something like, if a test taker scores 68.4, then that test taker is placed into the 33rd percentile, which means that that test taker scored better than 33% of all other test takers, and they did worse than 67% of all test takers. Okay, the last part of this question here says 50 different subjects are randomly selected and tested. Find the probability that the mean of the sample of 50 is below 71. So the idea here is that we have this bell curve, but the variable of interest is no longer x, but it is x bar. And the distribution of x bar follows a normal, and the mean of all possible x bars is actually equal to the population mean, and the standard deviation of all possible samples of size 50 is equal to the population standard deviation divided by the square root of the sample size. So this tells us that the mean of the sampling distribution of x bar is 75 mu, and the standard deviation is equal to 15, which is the standard deviation, over the square root of the sample size, which is square root of 50. And what we want to know, find the probability, so the mean is 75. That's going to be right here in the center. We want to know the probability that if we take a sample of size 50, what is the probability that the average of our 50 subjects is less than 71. So let's find 71, which is going to be over here. And we want to know what percentage of all possible x bars will result in an average that is less than 71. So let's kind of write that out. The probability that x bar is less than 71. Now again, what we have to do is we have to convert our boundary point. So let's convert our boundary point using the z-score formula. Z equals x bar minus mu x bar over sigma x bar. So this is going to be x bar is 71 minus 75, all divided by 15 over the square root of 50. And so when we compute this value here, you should get minus 1.89. And so what happens is we convert x bar into z, and we convert 71 into minus 1.89. So we can use the table 5 to look up the z-score of minus 1.89. And when we look that up, we get 0.0294. Okay, next question will be a confidence interval question. So let's read through and figure out if we can decide if it's a confidence interval for the mean or confidence interval for the proportion. So Dr. Paul O wants to estimate the mean serum HDL cholesterol for his 20 to 29-year-old male patients. He collects a sample of 40 of his patients and finds the mean of the sample to be 48.3 and the standard deviation to be 12.5. Construct a 99% confidence interval for the mean. So again, this idea of the mean wants to estimate the mean, tells us that we are doing a confidence interval about the population mean mu. Okay. Now, what we're going to do here is we're just going to pick out the pieces, the information that we need. Of course, the formula, x bar plus or minus t alpha by 2 times s over the square root of n. You can use this formula. However, I'm going to use the TI calculator to calculate this confidence interval for the mean. So let's go over here and jot down the information. Let's go over here and look at the calculator. And let's see what we need to know. So I'm going to go to stat, and then I'm going to go over to test, and then I'm going to do a scroll down until we find T interval. Now you can choose from data or stats, and this question here gives us the summary stats. So let's go down and plug in the sample mean. So let's go through and the question and see if we can find the sample mean. So he collects a sample of size 40. So 40, this is little n, this is the sample size, and finds the mean of the sample to be this. This is 48.3 is x bar, and that's what the calculator is asking us for. And the sample standard deviation is 12.5, and that's s. So let's type in 48.3. 48.3, and S, the sample standard deviation, is 12.5. And of course the sample size, we've already found that to be 40. And the confidence level is 0.99. It's really nice, this TI calculus. So now all we have to do is hit enter. Okay, and and then calculate. Of course, we'll hit enter again. Okay, so we get the interval 42.948 to 53.652. So and this interval here, I think I've got enough room, 42.948 to 53.652. And the interpretation of this is, we can say something like the true mean serum HDL is somewhere between 42.948 and 53.652 with 99% confidence. Okay, next question. Again, this is a confidence interval question. Many people think that a national lobby successful fight against gun control legislation is reflecting the will of a minority of Americans. A random sample of 4,000 citizens yielded 2250 who were in favor of gun control legislation. Estimate the true proportion of all Americans who are in favor of gun control legislation using a 95% confidence interval. So this is a confidence interval for P, the population proportion. And again, we're going to use the TI calculator to do this. And so we really just need to know the idea of P hat plus or minus Z alpha by 2, P hat 1 minus P hat over N. You can use the formula here, but I'm going to use the calculator for this confidence interval. So P hat, we really just need to know X over N. So X is 2250. And N, the sample size, is 4,000. And those are the only two numbers that you need to know for the calculator. So it's a really nice procedure that they have in the TI calculator. So let's go over here, see if we can pull it up. We'll clear everything out. We'll go to Stat, go over to Test. And this is going to be a 1 proportion Z interval. And notice all they're asking you for is X, which is 2250. And N, the sample size, is 4,000. And the confidence level is 95.95. And then calculate and enter. Okay. So we get the lower bound and upper bound. So let's kind of jot that in. 0.54713, and the upper bound is 572. 787. So we can say something like, we'll say it a little differently on this particular question. We'll say something like, we are 95% confident the true proportion is somewhere between and I'll just round here maybe to 3 decimal places, somewhere between 54.7% and 57.8%.